Welcome back, everybody. So that's the next morning session. And let me introduce the next speaker, who is Michael Dozer from different institutes. He is from CERN QTI. He's also taking care of the uh, quantum sensing part of the CERN QTI, and this was mentioned also by Sophia before. Michael, can you reduce a bit? Yeah. Okay. So it's very hard to speak with this echo here. So Michael is a senior research physicist who has been active mainly in the field of antimatter physics. He was a co-founder and the spokesperson of the AGIS experiment at CERN from 2010 to 2022. And this was the experiment which was assumed to measure the gravitational field acting on matter and antimatter, which is quite interesting by itself. And of course, the second leg of this study is to have more and more sensitive sensors and detectors, and this is how relates to the quantum sensing, which could be the future of this kind of experiments. So now this is the DRD5 collaboration with 112 institutes is the one who attempting to get the next level of quantum sensing. So this is about Michael. And now let's turn to the quantum detectors for particle physics and talk by Michael, who couldn't manage to come, unfortunately, but maybe next time he will join us. So Michael, the stage is yours, please.
Thank you very much for this opportunity to talk about something that I've spent quite some time in recent years pushing and discovering, namely quantum detectors for particle physics. It's unfortunate that I couldn't come to Hungary this time, but I will try to give you an appreciation of what this is about. And I will be focusing, and this is a little bit outside the topic of the GPU day, on quantum sensors for particle physics, both high and low energy particle physics. So I need to explain quickly what the terms mean, what quantum sensors mean, and then I'll talk a little bit about what applications quantum sensors can have in studying low energy particle physics, but also high energy particle physics. And then I'll give a short overview of what the landscape looks like worldwide in terms of research on quantum sensors for particle physics. So first of all, a quantum sensor is a device or a system that registers a change of quantum state caused by the interaction with an external system. So this can be a transition inside an atom from one energy level to another. It can be a transition in superconducting sensors from superconducting to normal conducting. It can be a change of resonant frequency in a system in a quantized manner. So it is basically the idea of a qubit, but expanded somewhat. And with that in mind, a quantum sensor is a device, the measurement and sensing capabilities of which are enabled by our ability to manipulate and or read out its quantum states. And I deliberately chose the or because you'll see later on that for high energy physics, we cannot read out the quantum states, but we can manipulate them possibly and manipulate then their functionality in terms of a larger detector, as elements of a large detector. And because these energy changes in a quantum state are very low, they're ideally matched, these quantum sensors are ideally matched to low energy particle physics, but I'll touch both on low and high energy particle physics. What I will not be talking about is entanglement. This is still beyond what we can achieve for macroscopic ensembles of quantum sensors, and that is what would be needed for high energy physics detectors. So if I think of measuring or using a sensor to measure the energy deposited by a particle in a detector, I have to really think of different layers in terms of what a sensor needs to measure. If I have a particle, a charged particle going through a liquid detector or bubble chambers or gas, but also ionization detectors and semiconductors, I'm typically looking at energy deposits of the order of electron volts or more. And there, silicon, germanium, gallium arsenide, quantum dots also are ideally suited. But if my energy deposit is going to be less, for example, if I'm looking for dark matter or recoiling nuclei, I will get energy deposits of the order of tens of milli-electron volts or even below milli-electron volts. And there I can then try to find technologies that are well suited to those energy deposits whose energy gap in a quantum system corresponds to that energy deposit. So for 10 to 100 MeV, it could be gallium arsenide, sapphire, Dirac materials, or doped semiconductors. In the case of milli-electron volt energy deposits, I really have to go to superconducting systems and look in superfluids and superconductance. So one really has to think about what the goal of the sensor is, whether it is to measure the energy deposited by known particles, minimum ionization, or to be sensitive to sub-minimum ionization energy deposits. So depending on what one wants, one or different technologies will be appropriate. And here's an overview of the kinds of technologies that would fall under the realm of quantum sensors to look for dark matter candidates, where the energy deposited inside the sensor then depends very much on the type of dark matter and its mass. To the left-hand side are the low energy particle physics quantum sensor types of detectors. And you'll see there's a whole zoo of different types of approaches. To the right, in the pink area, more or less, is where high energy particle physics would live, with light or heavy or ultra heavy dark matter particles, then depositing massive amounts of energy. And nevertheless, in spite of these very large energy deposits, you can see that also in that range, there are a number of quantum systems, for example, nitrogen vacancy diamonds, quantum materials, nanowires, that have the potential of playing a role in enhancing the functionality of those detectors. So what we did a few years ago is to go through all possible quantum technologies and look for those that are most suited for particle physics. And the 6 technology families that we focused on are shown on the left-hand side. They consist of superconducting devices like transition edge sensors, superconducting nanowire single photon detectors, and also the cryo-electronics that goes with it. So amplification, signal processing, ASICs at a few Kelvin. The second family has to do with spin-based systems, nitrogen vacancy diamonds. The third has to do with clocks and frequencies. The fourth has to do with ionic atomic molecular systems. The fifth has to do with optomechanical sensors, so where one couples mechanical changes to optical signals and vice versa. And the sixth has to do with engineered materials, metamaterials, and low-dimensional materials, 0, 1, 2-dimensional materials. And with these different families of quantum sensors, one can cover large domains of physics, be it searches for beyond the standard model physics or new types of physics, searches for dark matter in form of axions or axion-like particles, but also non-dark matter ultralight particles like milli or microcharged particles. Then tests of quantum mechanics itself, for example, trying to understand the process of wave function collapse, of decoherence, trying to test fundamental symmetries, the weak equivalence principle being one of them, but also tests of QED, of strong interaction, of parity, time invariance, charge parity, Lorentz invariance, and for example, doing this through electric dipole moment searches. And then finally, of course, all of these families can lead to new types of detectors. And so one also has to keep in mind that one wants to develop new types of detectors. And so I'm going to give a ridiculously rapid overview of a selection of particle physics at low energy that these quantum sensors are well suited to. And I'll focus on those that CERN has a particular involvement in. You just heard about CERN's QTI program. These 3 systems, so radio frequency cavities and cryodetectors for dark matter searches, atom interferometry clocks and networks for dark matter and gravity searches, studies, and exotic systems for beyond the standard model physics searches, tests of QED, tests of gravity, tests of symmetries, and dark matter searches. All of these fall under the CERN QTI-2 program with a main focus on sensing, but also in some cases the possibility of developing new types of qubits. And I'll mention those as I go through these different types of approaches. The first area I'd like to quickly talk about has to do with radio frequency cavities, which can be used to couple a hypothetical particle, the axion, to modes of the cavity, and then have this coupling produce a visible particle, a photon. So in the bottom right, you can see this axion coupling to the magnetic field of a cavity sorry, within which the cavity is situated. And this coupling to a photon produces a visible photon that can be detected, the upper gamma. Now, up to now, these radio frequency cavities have only searched for axions in a very narrow mass range. That's the blue bar around 1 microelectron volt. And the problem is that these cavities have limitations. The figure of merit of a cavity is proportional to the coupling of the axion to photons. That's the GA gamma squared, to the square of the mass of the axion, to the fourth power of the magnetic field. So these are embedded in the strongest magnetic fields one can build, to the square of the volume of this cavity, and then to the inverse square of the temperature of the cavity and to its quality factor. And if I want to go to lower axion masses, so for example, nanoelectron volts, picoelectron volts, to the left of that search window, while keeping the figure of merit constant, I have to make sure that as the mass goes down quadratically, the other parameters increase quadratically. And you can see that, for example, the volume, if we need to increase the volume quadratically to go down by 1 order of magnitude, we have to have a 10 times bigger volume. One very rapidly runs into problems with the cryogenics, which is a crucial element as well. So this is why this window is as small as it is. And to get around that, there's been the proposal to produce cavities that have multiple excitations, not just one single resonant mode, but two resonant modes. Here, these resonant modes are indicated as omega 0 and omega 1. And if one chooses the omega 0 and omega 1 such that their frequency difference corresponds to a specific mass, then that cavity is sensitive to that particular axion mass, which would then couple signals that, or power that is injected into the pump mode into the signal mode. In order to do that, one needs to build these cavities with multiple modes. And so one needs to design a cavity that is not only compact, but also has multiple modes. And you can see right away that if I want to scan several different masses, I can either build multiple such cavities, or, and this is the critical element here, engineer the cavity such that I can change the splitting between these two modes. So I have to have some kind of tuning possibility in addition to the two modes that allows then to scan a certain mass range. And this can be done either through mechanical deformation or through the tuning of the fields through superconducting RF cavities. So the cartoon you see on the bottom right corresponds to what one wants to achieve and where one wants to be able to change the resonant frequencies of these cavities. And this is being done right now at CERN by superconducting RF cavities. These two resonant modes can also be thought of as two energy levels of a qubit. And so in a way, this might allow building tunable splitting qubits in the future. The atom interferometry side of things is looking at something completely different. There, one is really looking at quantum mechanical interference processes within atoms. And the goal here is to use these atom interferometers, which have been built using high energy physics engineering approaches in a more or less cookie cutter manner now by the ION collaboration, with the goal of studying, on one hand, gravitational waves, and on the other, searching for dark matter and testing fundamental symmetries. So right now, this low mass region that is difficult to reach with the resonant frequency cavities can be searched with atom interferometers. But their sensitivity increases also dramatically if one builds them bigger and goes to very large separations. And the goal of this approach is to try to scale up from the existing cookie cutter atom interferometers, which have a size of about 1 meter, to the next step, which is to go to about 100 meters atom interferometers, before then going in a longer term to atom interferometers in space. And so there are two things that need to be done in parallel. On one hand, one needs to build bigger atom interferometers. This is being done within the ION collaboration, but also via the MAGES collaboration at Fermilab and several other atom interferometer scaling up approaches. But it's also being done at CERN. There's one attempt to move the ion atom interferometers into the vertical shafts of CERN, to the vertical shafts that allow access to the LHC, which have a depth of about 100 meters. If the FCC were to be built, it would even allow a 500-meter vertical ideal testing ground. And it builds then on the expertise that CERN has in cryogenics, vacuum, and complexity. In parallel to that, one needs to make sure that these atom interferometers are stable and reliable. And so one of these has been launched just very recently, a month ago, to the International Space Station and switched on shortly afterwards. If these two approaches work out and one can really have reliable, stable, maintainable at distance devices, then the goal is to go on a timescale of about 20 years from now to satellite missions with a series of atom interferometers separated by very large distances and trying to measure gravitational waves that would lie between LISA and LIGO. And the third area of low energy particle physics that I want to briefly touch on has to do with exotic systems, either individual charged particles like antiprotons, which have already been used again in an approach similar to that of radio frequency cavities, but this time in a dedicated experiment, an experiment dedicated to something completely different, to exclude axions at a very low mass, nano electron volts, so about 1,000 times lighter than the usual radio frequency cavity window. And this can be expanded. You can see the plot on the bottom left side to a much larger mass window through optimizations, cryogenic electronics in particular, but also to be able to produce systems that are exotic in a different way. For example, trapped ions, highly charged ions, with a very large sensitivity to variations of fundamental constants than current clocks achieve. And these systems can consist of a bare nucleus with a single electron. The reason why one wants to investigate those is that many of the interactions that atoms have, optical interactions, are pulled very deeply into the UV, and microwave interactions that atoms have are pulled into the optical range. So in the case of boron or argon-13 here, one can compare the energy levels and can see that the hyperfine splitting of boron, which is a completely filled atom of around 650 micrometers, that transition is shifted into the optical range at 440 nanometers, so in the green wavelength, in the case of the analog to boron of argon-13+, so argon where 13 electrons have been removed. The interesting point here is that these atoms have a very small sensitivity, or these ions have a very small sensitivity to external electric fields, and so one can think of using them to build very insensitive types of qubits. And the way one can do that is by starting out with using and building antiprotonic atoms, whereby an antiproton is used to remove all the electrons of a normal atom. The antiproton in step 3 annihilates on the surface of the nucleus, removes a proton or a neutron. The remnant nucleus can be trapped and cooled, and then one can attach a single electron, that's the middle bottom sketch, to this system where one has a novel type of highly charged ions in a Rydberg state. But once the electron has cascaded down to the ground state and the electron is practically at the surface of the nucleus, one actually has a novel type of qubit where the spin of the electron pointing either up or down has two possible values, and this kind of qubit should be extremely insensitive to external perturbations. Naturally, from a particle physicist's point of view, one would like to not only attach an electron and study electromagnetic interactions, but also an antiproton, and this is something that can also be done via the same approach, and that would allow then testing the strong interaction and looking whether the strong interaction holds at long distances as well as short distances. So these are completely new systems that CERN is trying to build up at low energy. At high energy, we have the problem that, of course, these quantum systems don't scale very nicely to the number of interactions that a particle and a detector have to have so that one can measure the properties of the particle, which typically rely on ionization, many ionization steps of a particle going through a detector, many scintillation processes where one produces large amounts of light, or Cherenkov processes where again one produces many photons. Now, there are a handful of ideas that rely on quantum systems, individual quantum systems, that are embedded into a larger system and that are not quantum detectors per se, but that have properties that enhance the properties of the detectors, or maybe even allow measurements that are more difficult to achieve otherwise. So I'll say a few words about how these quantum systems can be used in a bigger context to achieve tracking, calorimetry, timing, novel observables. And I have to warn you that these are very speculative ideas that are only starting to be investigated. And so I'll talk about four different types of sensors: metamaterials, low-dimensional materials, atomic systems, spin-based systems, and superconducting sensors. The first one, the low-dimensional materials, is ideally considered in terms of quantum dots, so an assembly of a few hundred atoms that is shown in the middle as these triangular structures. They really correspond to the assembly of these atoms. And the fluorescence properties of these quantum dots with specific geometries and compositions are very nice because they emit very narrow band light. You can see at the bottom right and just above it the fluorescence light that these quantum dots emit, and they are very pure. This is very narrow band. It's about 20 nanometer bandwidth of the emission. And the most important point is that these emission spectra are shifted with respect to the absorption spectra of the same quantum dots. So once a photon has been emitted, scintillation photon has been emitted by a quantum dot, even if that quantum dot is surrounded by many other identical quantum dots, those will not be able to absorb that photon. And this allows conceiving of building a calorimeter, a device shown at the bottom right, where one has different layers of high density material which emit light at different frequencies. This is material where quantum dots are either on the surface or in the bulk. And any photon produced as a charged particle comes in will propagate to the end. But depending on where this interaction happens, the color of that propagating photon will be different. So if an incoming particle produces a shower of different particles inside this calorimeter, the spectral distribution of the photons that are produced in the different layers will allow one to reconstruct the shower profile that the incoming particle has produced and thus identified in a way that is new. This is not something that current calorimeters can do. Now, these ideas have been tested in two ways. First of all, via simulations. The left-hand side of the slide corresponds to Géant 4 simulations, where one has either embedded quantum dots or put thin layers of quantum dots at the surface of different layers, and then measured the color composition at the end of this stack in the photon detector. You can see a picture of what such a simulation looks like with an incoming electron producing many secondary particles in the shower in the different layers, and you can see the intensities of the different colors. At the bottom is shown the relative light yield of the red, the green, and the blue light that is produced in such a simulation as a function of the energy. The energy of the incoming particle will define how deep it goes, and so how much red light there will be. Initially, low energy particles will all stop inside the red block. Higher energy particles will go deeper. Even higher energy particles will go even deeper. And so the relative ratio, the ratio of the red to the green to the blue will allow one to measure in some way the energy of the particle. And this can be done already just based on the relative yields. If one goes even further not with simulations, but with actual real devices that approximate what a quantum dot doped detector would do, one can see in the top right, middle right, a device that was actually put into beam of pions and electrons. And at the bottom, one sees the outcome of this test, the intensity of the blue light coming from the far right side of this stack versus the intensity of the yellow light, which comes from the far left side of this stack, depends on the particle type and on its energy. And this ratio can then be used, as you can see in the bottom right plot, to discriminate between electrons and pions, just purely based on the color of the light that is emitted by this calorimeter. This doesn't at all use the fact that one already has measurements from other detectors, or that one measures the totality of the light emitted by the scintillators. It's just purely the ratio of the blue to the yellow. One can go one step further and try to build active scintillators, for example, by embedding quantum dots inside a gallium arsenide device, as shown on the right-hand side. This is a so-called dot-pix device, whereby quantum dots that a charged particle interacts with emit scintillation light, fluorescence light, and this scintillation light is immediately picked up by quantum photodetectors on top of the slab itself that contains the quantum dots. And this device is currently, as shown at the bottom right figure, one of the brightest and fastest scintillators. And if one improves its properties by another order of magnitude or so, it will be not only the fastest scintillator with decay times of the order of 100 picoseconds, but also the brightest scintillator. And this is something that would allow building, well, basically optical trackers, a way to optically, through photon emission and photon detection, measure the position of a charged particle as it goes through a device. So it goes away from the silicon trackers to photon trackers. Using atomic physics is difficult in high-energy physics, but there is one way to do that, and that might work by tuning so-called time projection chambers. These are big cylinders that are filled with gas, and on the left-hand side of the picture, you can see what happens when two particles collide, produce secondary particles that go through the gas volume. These secondary particles will ionize the gas, releasing electrons from the gas, and in an electric field between the two plates of this cylinder, the electrons are drifted towards one end until they enter a so-called amplification region, where a very strong electric field accelerates them to such energies that they can ionize in the gas there in turn. And this chain reaction produces an avalanche of electrons that can then be detected on the final plate in time and in position. Now, if one reduces the energy needed to ionize the gas in that region by exciting the atoms from the ground state to an excited state via lasers, then one can have a bigger avalanche or the same avalanche with a smaller electric field. This would allow to get a higher signal, a cleaner signal, and it would also allow working with lower electric fields, which solves another problem, which is that the ions that are left over after an electron has been ripped away from the atom, that ion can drift into the drift volume and then capture electrons that come from the next interaction, so poisoning that drift region. This should allow reducing the poisoning effect as well. So stronger signal, cleaner signal, and less electron losses. One can also think of using solid state devices like nitrogen vacancy diamonds, which are also being used as qubits, to polarize a large fraction of the carbon atoms inside the diamond. This is already being done, as one sees on the left-hand side, to produce spin-polarized marker molecules, whereby one uses nitrogen vacancy diamonds that are polarized with microwave light, such that the surface of these diamonds becomes polarized as well, and these randomly oriented marker molecules interact with the surface polarization to then become spin polarized. Whether one can use this for high-energy physics is an open question, but if it is possible to polarize a significant fraction of the bulk of the diamonds, something like 10% of the diamonds, then one could think of building an intercalated structure, a sandwich structure between tracking detectors, silicon trackers that measure the position and the direction of a charged particle with these polarized planes, which then will scatter that particle depending on the relative orientation of the spin of the particle and the polarization of that plane. And by building up a series of multiple scattering measurements, one can determine then the initial spin of that particle. This is something that is currently impossible to do, and this kind of detector might then enable a new type of measurement. And then the last category of devices I quickly want to mention have to do with cryogenics. These are nanowires, very thin wires that can absorb single photons. These are often used in quantum cryptography to detect the two photons that are emitted back to back. In this case, we don't want to use the photon sensitivity. We want to use the sensitivity to charged particles. The functionality is the same. As energy is deposited inside these nanowires, they heat up. The current that is flowing stops. So there's a voltage pulse that is produced, and this voltage pulse's duration is given by the time it takes that nanowire to cool back down again. So this sensitivity that these devices have is of the order of 100 millielectron volt energy deposit on a thickness of 10 micron. And the hope is to improve this by a factor of 10, so to 12 millielectron volts over 100 micron. And this has to be compared with the energy deposited by a normal charged particle on the same length scale, which is around 20 kilo electron volts, so about 1,000,000 times more. And what this means is that these devices should be very sensitive to particles that have very little charge, so deposit very little matter, hypothetical particles, so-called milli-charged particles. And one could use these to build a tracker, a stack of these, of pixelated devices, could build a tracker for milli-charged particles that could be detected in experiments behind a beam dump, so where huge numbers of particles are shot into a target and the resulting secondary particles are absorbed, except for these milli-charged particles and muons, which would then allow calibrating the whole device. The same detectors can also be used because of their very fast decay and rise time and decay time of the order of a picosecond, and their high temperature behavior to look for particular collisions inside LHC experiments, so-called diffractive scattering, which would allow picking out with picosecond precision two charged particles that basically graze each other and scatter at a very small angle. Because of this very high time resolution, all the other particle collisions that come out of that particular collision time can be filtered away, and one should get a very clean signal in the tag for these types of events. And the last superconducting detector I'd like to quickly flash at you is a transmon that is at the heart of Google Sycamore processor. What was done in this measurement is to take an array of transmons, a pixel array, and to investigate the simultaneous qubit errors as a function of time. So basically taking snapshots and look where the errors occur if they occur. And what was found in this case is that if one looks at the time sequence 1, 2, 3, 4, that these errors are not uncorrelated. They actually cluster locally inside an area that matches perfectly well what one expects to see if a charged particle, a cosmic ray, would traverse the device and deposit energy in the transmons themselves. So in a way, this is an indication that transmon arrays can also be used to detect charged particles, although only at a very low rate. This is a time rate of about 100 milliseconds. So they're not quite there yet in terms of charged particle detectors. Now, I've shown you the technologies, I've shown you the applications. I'd like to say a few words about the landscapes and the ambition for these detectors. The 6 families of detectors that I have mentioned, or quantum systems, have all been looked into in the framework of a roadmap to see what one could achieve on a time scale of 20 years from now. And if one carries out the necessary R&D on these individual detectors, pretty much all these families can play a role in not only building functional high-energy physics detectors, this is what I've tried to show you here, but also in trying to build space-based sensor networks, that would be the atom interferometry, to investigate dark matter, assuming that we have found that it is light, but also to look for relic neutrinos from the Big Bang. These are very ambitious goals, but they are reachable on a timescale of around 20 years from now, assuming that R&D on quantum sensors is carried out. And so 2 years ago, we submitted a proposal in the framework of CERN's detector R&D process to facilitate the necessary R&D. We reformulated these families into work packages, 5 work packages having to do with technology, 1 having to do with capacity expansion. We wrote a proposal on a timescale of a year in 2023, were approved in the summer of last year, and have formally constituted the collaboration in October of last year. This is the DRD5 collaboration working on 6 work packages with a very lightweight management structure, different working groups on the different technologies. And the outcome of this R&D is for this year, basically to work on workshops that identify common problems for that particular technology in that community, to prepare detector test facilities, to try to synchronize R&D across different groups, to work on educational aspects, so to try to train a workforce in quantum technologies, and to work towards agreements and standards so that different groups in different countries can collaborate more easily and use each other's infrastructures. The collaboration is now consists of 112 groups worldwide. You can see here the list of all the institutes. The focus of the different groups matches very nicely the different work packages. We have a more or less even distribution of interest in different physics topics. And as a last slide, I'd like to just summarize by saying that this collaboration is being ramped up. It combines different communities, including high-energy physics communities, but not only. We have many novel developments that will benefit both quantum technologies and particle physics. And most importantly, it's free. Anybody can join. And with that, I'd like to thank you for your attention.
Thank you very much, Michael, for this nice and comprehensive view of the quantum sensors. Any questions from the audience? I know this topic was slightly away, but this is the thing which I think is very important to see, that where quantum technology could develop. If nobody else wants to ask, yeah, Sophia has a question.
Sorry, Michael.
Hi, Sophia.
I've asked many times, but I actually never did. So do you know if there are problems in simulating any of the physics processes that describe the behavior of those detectors?
Absolutely. So we don't have a good model for example, these quantum dots. What actually happens, how to optimize them, what effects play a role in the quantum dots, geometry, in the composition, in their size, in terms of fluorescence processes. We need solid state physicists to look into that. And part of it really has to do with computational problems. It's a very similar problem for the atomic systems. Right now, we're preparing a workshop on identifying the challenges to bound state calculations. This turns out to be the biggest challenge right now. So these are complex calculations that try to not only look at the existing systems like hydrogen, which is a very simple system, but multi-body systems going all the way up to molecules, including different kinds of participants, antiprotons, muons, pions inside the molecules, to try to see their sensitivity to new physics. So computational challenges are at the heart of this collaboration, just as theory is and as hardware is.
Thanks.
Anybody else? So then I also have a question. So you mentioned that one of the point in the very last slides, you mentioned that milli-charged particles, so very, very low charge particles can be measured. Is there any chance to measure pure neutral particles, which has zero charge at all, which is a key point because
Mm.
times it wants to measure zero charge particles have to transform to charge one at the end of the day. So do you have any points on this?
So it depends on the neutral particle that you're looking at. If it's a photon, we can build these calorimeters, these chromatic calorimeters. That would be one way to see the neutral particles. But I think you're thinking of something else.
Yeah, massive particles. Like
Massive particles. So there you have to have some interaction either with the electrons or the nucleus of the detector. And most of the time, what you're thinking of is particles that have a very low interaction rate. So you need massive devices to have a probability, like for neutrinos, to interact at some point. So what I see, and we're looking into that as well, is to combine massive stopping power in high Z materials, for example, with high sensitivity materials right after that that would be able to detect a nuclear recoil or low energy electrons. The scaling up of a small lab device to the macroscopic dimensions that you need for that is the big challenge we're trying to address. And there we need probably more input from both the theorists in terms of what types of interactions one would want to look for, as well as from experimenters trying to see how one can combine highly sensitive detectors with massive material right next to it, multiple sandwiches. This is really a material science challenge.
okay.
But yes, it's definitely on our roadmap.
Yeah, I think that would be very, very interesting for the wide community,
Mm.
heavy ion physics and high energy physics. Okay, any further questions or remarks? Okay, if not, let's thanks Michael again.